My name is Shahroz Ahmed, and in this video we'll discuss about the waves. Basically, we'll discuss about the transverse and longitudinal waves. So let me start off by the definition of waves. So waves, it's a medium that transfers energy from one point to another. So I write it here, a medium that transfers energy from one point to another. One point to another. We have let's discuss some attributes of a wave. So let me just draw a wave over here. So this is the y-axis, and over here I have the x-axis. In the x-axis direction I have the time, and the y direction I have the displacement. And the unit of displacement is meters. For the time it's seconds. Now let me just draw a wave over here. So this is the wave. Okay, now let's discuss the first point, that is displacement. What is displacement? Displacement is basically, it is the distance from the equilibrium position or the mean position. Over here you can see this pink line. This pink line is basically, it's the mean position. So let's suppose I want to find out the displacement at any point on the wave. For example, I want to find out the displacement at this point, or at this point, or at this point. Then the distance from the equilibrium position is called the displacements. So for this point, my displacement will be this much. So let's suppose over here I have some value. Let's suppose it's 5 meter. So this will be the displacement. Over here, this will be the displacement. And for the third point, this will be my displacement. So I can write for the displacement as the distance from the equilibrium position from the mean position. I'll write mean position is displacement. Now the next thing that we have to discuss is amplitude. So amplitude is basically the maximum distance covered by a wave from its mean position. I'll write it here, amplitude, the maximum distance of a wave from its mean position. That is the amplitude. So my amplitude will be here, this one. This is the maximum point, this is the negative maximum point, this is another maximum point. So the distance from the mean position to this point will be my amplitude. So this will be my amplitude. Alright, so these distances will be my amplitudes. Okay, now the next thing that we have to discuss is the time period. Let me just erase it. So alright, so the next thing that I have to discuss is the time period. So let me just write down the definition first. So time period is basically, it's the time taken by a wave to complete one cycle. The time taken by a wave to complete one cycle. One cycle is the time period. Now, for example, my cycle of the wave starts from this position, this point, and it ends at this point. So the time that it takes for the wave to complete one whole cycle is called the time period. So the time from this position to this position is the time period. So this will be my time period, and I'll represent it with capital T. And it is represented by capital T, and its unit is second, that is represented by small s. So these are the three first attributes of the wave: displacement, amplitude, and the time period. Now the next one that we have to discuss is the frequency. So let me just erase it. So frequency is related to the time period. So let me just write down the definition first, and then I'll explain you and show you the relationship between the frequency and the time period. So frequency is basically the number of cycles of a wave passing through a point in 1 second. Passing through a point in 1 second is the frequency, and we represent the frequency in hertz. This is the unit of frequency that is represented by Hz. Now the relationship between the frequency and the time period is frequency that is represented by small f. It is equal to 1 over time period. So this is how we represent frequency. Now after the frequency, we have to discuss the wavelength. So for that purpose, let me just erase it. Alright, so for the wavelength, we will have distance in the x-axis and displacement in the y-axis. Now this point is called crest. The maximum displacement point of the wave is called crest, and the negative maximum displacement point of the wave is called trough. Alright, so wavelength is basically, it is the distance between two consecutive crests or between two consecutive troughs. So from here to here, it will be a wavelength, and we represent wavelength by a symbol that is called lambda. So this is the symbol. So I'll write down the definition over here for the wavelength. So wavelength is the distance between two consecutive crests and or two consecutive troughs. Between two consecutive crests or two consecutive troughs. Alright, so now we represent wavelength by this symbol. After this, we have to discuss the relationship between the speed of the wave, the wavelength of the wave, and the frequency of the wave. So for that purpose, I have to explain about the speed of the wave. So if we have to determine the speed, so speed is simply, we can say it is the product of frequency and wavelength. So the speed is the product of frequency and wavelength of a wave. So we represent speed with v. So v is equals to f lambda, where f is the frequency and lambda is the wavelength, and v is the speed. The unit for the speed that we use is meters per second. Alright, now the next most important thing that we have to discuss is the phase difference. So phase difference. So in simple words, if I explain the phase difference, it is basically, phase difference is the measure of how much a wave is in front or behind than the other wave. So I'll write it here. Phase difference, it is the measure of the difference of how much our wave, how much our wave is in front or behind the other wave. So let me just draw two waves over here with the zero phase difference. Then I'll draw two waves with a phase difference of quarter of wavelength. Then I'll draw waves with a phase difference of half of the wavelength, and waves with a phase difference of full wavelength. So let me just draw two waves over here. So this is my y-axis, this is the time over here, this is displacement, and in the x-axis we have the time. So let me just draw the first wave. So here I have the first wave. Okay, now let me just draw the second wave. So my second wave has started from the same position where the first wave has started. This black wave has started from the same position where the blue wave had started. So there is no phase difference between these two waves. Remember that in one cycle starts from this point and ends over here. In one cycle there are 360 degrees or 2 pi radians. A quarter cycle is of 90 degrees, a half cycle is of 180 degrees, 3/4 cycle is of 270 degrees, and a full cycle is of 360 degrees. So we'll be using that in the next step. So now in these two waves there is zero phase difference. Now I'm going to change this black wave. So now instead of starting from here, the black wave has started from this point. So now, as you can see, it has the same frequency, it has the same time period, but the only thing is that the black wave has started after a quarter cycle. Now you see the difference between the starting point between these two waves differs by a quarter of a cycle. So we can say there's a phase difference of 90 degrees or pi by 2 radians. Now let's start off with the black wave that will start from this position. So now my black wave is starting after a half cycle. So it will start from here, complete half cycle, complete full cycle, half cycle, next cycle. Alright, so now you can see the difference in the starting point of the two waves. The black wave has started after a half cycle, so we can say the phase difference between them is 180 degrees or pi radians. The next thing, now my black wave will start from this position, and similarly it will grow like that. Alright, so between these two waves now the phase difference is 270 degrees or 3 pi by 2 radians. And when my black wave will start from this point, then the phase difference will again become equal to 0 or 360 degrees. Now both the waves are in phase, they are starting from the same position. The only difference is that the black wave is starting after exactly one complete cycle. So over here the phase difference is 360 degrees, but they are in phase. Okay, so for this one, when my wave was 180 degree, the waves was completely out of phase. The waves were completely out of phase. And when my angle is 360 degrees or 0 degrees, the wave will be considered as in phase for 0 degrees and 360 degrees. And for 90 degrees and 270 degrees, my waves will be considered partially in phase and partially out of phase. So for the introductory purposes, I think this is fine in order to understand the phase difference. All right. So now the next thing that we have to discuss is the transverse and the longitudinal waves. So it's quite simple concept. Transverse and the longitudinal waves. So what happens is, as we have discussed, that the waves are produced by some vibration in a medium. When that vibration is perpendicular to the direction of wave, then such a wave is considered to be as the transverse wave. So let's suppose the wave is going towards right. This is the direction of the wave, and the direction of the vibrating medium is up and down like this. So you can see this is the vibration up and down, and the direction is towards right. So there's an angle of 90 degrees between them, so they are perpendicular to each other. So when this happens, then we say that the waves are transverse waves. And let's suppose the wave is going in this direction, and the particle is vibrating in the same direction, left right. This is the direction of vibration. So when this happens, then we can say the direction of the wave is parallel to the direction of vibration, so the wave is considered to be longitudinal. So such waves in which the direction of vibration is perpendicular to the direction of wave are transverse, and the waves in which the direction of vibration is parallel to the direction of the wave, such waves are longitudinal. So this one is the longitudinal, and this wave is the transverse wave. In the longitudinal wave, we see the compressions and rarefactions, and in the transverse waves, we see the change in the displacement of the wave. So for the longitudinal wave, we can consider the wave like this. There will be some compressions, there will be some rarefactions, again compressions, again rarefactions. So this is considered to be the longitudinal waves, and the sound waves are the longitudinal waves. And for the transverse wave, we can see the change in the amplitude. So let's suppose a wave is going like that. So this change in amplitude can considered to be in the transverse waves. And for the example purposes, we can say that all the electromagnetic waves are the transverse waves, because in electromagnetic waves, they are produced by when the direction of vibration is perpendicular to the direction of the wave itself. Okay, so this is it for the transverse and longitudinal waves. Now we have another concept that we have to discuss, and that is of the polarization. Polarization, it sounds to be quite tricky, but let me just make it easy for you. So polarization. Okay, so polarization, basically it occurs when particles vibrate in only one direction. For example, this is sun, and the light waves are coming from the sun that are not in one plane. So let's suppose we consider a photon of light that is coming from the sun, and this photon, the particles are vibrating in all the directions. So we can say that this is unpolarized light. Unpolarized light. So in order to make unpolarized light into polarized light, that process is called polarization, and a polarized light will be found when all the particles in the light will vibrate in only one direction. So over here you can see the particles are vibrating. Some particles are vibrating in the vertical direction, some are vibrating in the horizontal direction, some are vibrating in the directions at some angles. All right, so we will put a polarizer in between this photon, and we'll get and we will convert these particles to vibrate in only one direction. All right, so this is the light that is coming out from the sun. So what we do is we'll put a polarizer. So let me just draw it with this bluish color. So I have put this polarizer. So now let's consider this is the direction of the light. This is the direction of light. So I have put a polarizer. Now this polarizer it depends on this polarizer how it aligns the light. Either it could align the light in the vertical direction, it could align the light in the horizontal direction, or at some angle. So for this polarizer, let me just say that this polarizer will align the light in the vertical direction. So I'll just draw a vertical line over here. Okay, so now the light that I'll get as the output will have only one direction, and that will be this one. the vertical direction. Alright, now if I put a polarizer with the horizontal direction like that, then the light that I would get as the output will have only one direction, that will be in the horizontal, like this. Okay, now one more fact that you have to keep in mind for the polarization is about the intensity. After a light, when the light passes through one polarizer, through the first polarizer, the intensity of the light decreases by 50%. Okay, so I'll write it here. The intensity of light decreases by 50% when it passes through a polarizer. Alright, okay, now if I put another polarizer in front of this light, then let's see what happens. So if I put another polarizer, and that polarizer, let me just draw over here, so this is the direction. I'll just draw it again so I could save some space. So I'll put my first polarizer over here. This is my first polarizer, and I'll put my second polarizer over here. This is my second polarizer. Okay, so let's suppose after my first polarizer, that will align the light in the horizontal direction. So at this point, my light particles will be vibrating in the horizontal direction. When this light particle will pass through the second polarizer, so if second polarizer has the same alignment as of the first polarizer, then I'll get the particle vibrating in the horizontal direction. But if the alignment of the second polarizer is perpendicular to the first polarizer, like this, my second polarizer wants to align the light in the vertical direction. So as we know that there is nothing in the vertical direction of this light, so what will happen, we'll not see anything over here, so it's only a dot over here. So the intensity of the light will become 0 if the first polarizer is perpendicular to the second polarizer. So this is the concept of polarization, that we align the light only in one direction, and this is how we use the polarizer in order to align the light. So it is essential that the intensity of the light will fall by 50% after passing through the first polarizer, and it will remain 50% after passing through the second polarizer if the alignment of the second polarizer is same as of the first one. But if the alignment of the second polarizer is perpendicular to the first polarizer, then the light intensity will become 0. So this is the first polarizer, and this one is the second polarizer. Okay, so this is it for the polarization and this topic of the waves. Now I'll do an example question, and then this topic will be done. Alright, so let's do this exam related question. It says that figure 1 represents a progressive wave traveling from left to right on a straight string. Part A. The frequency of the wave is 30 Hz. Calculate the speed of the wave. So we have been given the frequency, that is 30 Hz, and we have to find out the speed of the wave. So we know that the equation for the speed of wave is V equals to F lambda. We have the frequency, but we do not have the wavelength. So what we do is we can find out the wavelength from here. So the length of 1.5 cycle is, in fact, up till here it's 1 cycle, and this is another quarter cycle. So the length of 1.25 cycles is 70 centimeter, and we have to find out the length of 1 cycle. So I'll write it here. 1 cycle, the length of 1.25 cycle is 70 centimeters, and we have to find out the length of 1 cycle. So I'll write it over here as x. I'll cross multiply them, so it'll become 1.25 x equals to 70. Now from here I'll get the length of one cycle, so that would be 70 divided by 1.25, so that would be equal to 56 centimeters. 56 centimeters. Now 56 centimeters will be equal to 0.56 meters, so I'll put 0.56 meters over here. So my speed will become equal to 30 times 0.56. So 0.56 times 30, that would be equal to 16.8. So 16.8 meters per second is the speed of this wave. So this is how we can find out the speed. Now the next question is, state the phase difference between points x and y on the string giving an appropriate unit. Okay, so we have to find out the phase difference between these 2 points. So this is the point and this is another point. So in order to find out the phase difference, what we do is we measure the length between the 2 points, divided by the wavelength and times it by 360. So I'll do it over here. So the length between these 2 points is 70, so I'll do 70 divided by the wavelength for one wave is 56 centimeters, so I'll divide it by 56 and I'll times it by 360 degrees. So I'll just do some working. 70 over 56 times 360, that would be equal to 450 degrees. 450 degrees. We can say that the phase difference between these 2 points is 450 degrees, or we can subtract 360 from 450, and that will also be considered as the phase difference between these 2 points, and that will be equal to 90. So both answers are correct, either 450 degrees or 90 degrees. Now after this one, let's move on to the next part. Let me just erase all of them. Okay, now the next part, it says describe how the vertical displacement of point x on the string varies in the next period. Okay, so we have to describe the vertical displacement of point x. So first of all, I have to identify where is my point x. So point x is over here, and the direction of the wave is towards right. The wave is going towards right. So let's suppose after a quarter cycle, what will happen when the wave will go to the right? So let me just make the pattern when after a quarter cycle. So after the quarter cycle, the pattern of the wave will be like this. It has traveled 90 degrees to the right after a quarter cycle. Okay, so point x will come over here. So we'll say after quarter cycle, or yeah, I'll say after 1/4 cycle, x will be at maximum positive displacement. Then I'll move the wave half cycle more to the right. So when my wave will move half cycle to the right, I'll draw it with this blue color. It will look like that. So now my wave has moved half cycle to the right. Let me just complete it over here. So now the point x will be at negative maximum. So I'll write here, after further half cycle, x will be at negative maximum. Okay, now we have completed 3/4 of the cycle. Now let me just draw the cycle when one cycle will be completed. So that point will be here. When a whole cycle will be completed, then the point will come back again to the same position where it started. So after one complete cycle, the point x will be at 0 displacement. So I write it here. After a complete cycle, point X will be at the same position where it started. So this is how point X will vary. After the quarter cycle, it will go positive maximum. After a further half cycle, it will go to the negative maximum, and after a complete cycle, it will come back to the same position from where it started. So now I'll move on to part D. It says determine the phase difference between the current position of X and the position of X 0.0825 seconds later. So alright, so in order to measure the phase difference, what we do is we will divide 0.0825 by the time period, and we'll get the number of cycles. So this will give us the number of cycles, and from the number of cycles we will get to know the phase difference. So from here I'll get the answer as equal to 2.5. So now after 0.0825 seconds, the wave has traveled 2.5 cycles, which means that the phase difference will be considered for the half cycle, because after each cycle the phase difference again becomes 0. So after one cycle the phase difference will become 0 degree, after two cycles it will become again 0 degree, and after half cycle the phase difference will become equal to 180 degree. So the phase difference will become equal to 180 degrees or pi radians. So this is how we can solve this exam related example. I hope you understood it. Thank you.